Welcome back. Last episode, the Fundamental Theorem of Calculus told us something extraordinary. To compute a definite integral, you don't have to grind out Riemann sums, you just have to find an antiderivative and subtract. Beautiful. Except in practice, the antiderivative is almost never sitting there waiting for you. Most integrands you actually want to compute look messy. They have compositions inside them, they have products, they have rational functions. Integration becomes a hunt for antiderivatives, and the whole rest of integral calculus, frankly, is a catalog of techniques for that hunt. There are two big ones, and they are the two big differentiation rules played in reverse. The chain rule, run backwards, is the method of substitution. The product rule, run backwards, is integration by parts. Today is substitution, next episode is parts. Derive the method from the chain rule, so you see exactly where it comes from. Show why the Leibniz differentials trick, that thing where you write du equals g prime of x dx and it looks suspiciously like cancellation, is actually a theorem, not a fudge. Work 4 examples. Handle definite integrals which have one extra wrinkle. And finish with a short guide to choosing u when nobody is telling you what to pick. Quick orientation before we dive in. Differential calculus had a handful of fundamental rules: power rule, sum rule, chain rule, product rule, quotient rule. The two structural ones, the ones that handle combinations of functions, were the chain rule and the product rule. Everything else is bookkeeping. Each of those two rules, when you run it backwards, gives you an integration technique. The chain rule backwards is what we're calling substitution, or u-sub. The product rule backwards is integration by parts. These are the two heavy lifting techniques in the integral calculus toolkit. Almost every textbook integral you'll meet falls to one or the other or some combination. Today, substitution. Start with the chain rule. If capital F and G are differentiable, and you set u equals g of x, then the derivative with respect to x of capital F of g of x is capital F prime of g of x times g prime of x. The outer derivative evaluated at the inner function times the derivative of the inner function. That's the chain rule. You knew it cold from differential calculus. Now do something that students rarely do explicitly: integrate both sides. The left side is a derivative, so integrating it just gives back the function. That's the Fundamental Theorem, part 2, doing its job. We get capital F of g of x plus c. The right side becomes the integral of capital F prime of g of x times g prime of x with respect to x. Now rename. Let f be capital F prime. So capital F is an antiderivative of f. Substitute and you get the identity that does all the work. The integral of f of g of x times g prime of x dx equals capital F of g of x plus c. That is the substitution rule. We just derived it from the chain rule. No magic. Here's the punchline, packaged. If your integrand has the shape f of g of x times g prime of x, then the integral equals, by the calculation we just did, the same integral with u equals g of x written in and du in place of g prime of x dx. So the messy x integral becomes a clean u integral. 3 steps in practice. Pick u. The inside of the composition is almost always the right pick. Replace. The integrand f of g of x times g prime of x dx becomes f of u du and you integrate it in u. Back substitute. At the end, you've got an answer in u. Plug u equals g of x back in and your answer is an x again. For indefinite integrals, you must back substitute because the question was asked in x. That is the whole technique. Pick, replace, integrate, back substitute. The art is entirely in picking u. Now a word about notation. You will see this written in a way that looks like algebraic sleight of hand, and I want you to know exactly why it works. Leibniz's notation writes the derivative as du over dx with du over dx as though they were separate quantities. They are not. Du over dx is a single symbol for the derivative. But Leibniz designed his notation so that you can, in many situations, get away with treating du and dx as if they were independent tiny quantities. If du over dx equals g prime of x, you can multiply both sides by dx and write du equals g prime of x dx. In practice, this is how everybody does substitution. You write down your choice, u equals g of x. You differentiate to get du over dx equals g prime of x. You write du equals g prime of x dx. And then inside the integral, every place you see g prime of x dx, you cross it out and write du. The composite f of g of x becomes f of u, and out pops a clean u integral. It looks like cancellation. It is actually the chain rule from the previous slide, exactly. The notation was designed by Leibniz to look like cancellation precisely because the chain rule guarantees the cancellation is legitimate. 3 centuries later, we still use it because it is unreasonably effective. Here is the recipe, one more time, in 5 steps you can run mechanically once you've picked u. Choose u to be the inside of the composition. Compute du as g prime of x dx. Substitute throughout the integral so that everything is in terms of u and du, no x's should remain. Integrate in u, which by assumption is easier than the original problem. And finally, back substitute. Replace u by g of x everywhere in your answer. That gives you an antiderivative in x, which was what the question asked for. For definite integrals, there is one optional shortcut. When you change variables, you can also change the limits of integration from x values to u values and just evaluate in u. We'll do that in a few slides. For now, let's actually use the recipe. First example, the cleanest possible. Compute the integral of 2x times cosine of x squared dx. Look at the structure. There's a cosine of something, and that something is x squared. So we have a composition with x squared on the inside, and this is the lucky part. The derivative of x squared, which is 2x, is sitting right there next to the cosine. The integrand is in exactly the shape the substitution rule was designed for. Let u equals x squared. Differentiate du over dx equals 2x, so du equals 2x dx. Now substitute. The x squared inside the cosine becomes u. The 2x dx becomes du. The integral becomes the integral of cosine u, du, with no x's anywhere. That's an integral you know cold. An antiderivative of cosine is sine, so the answer is sine u plus c. Last step. Back substitute. U was x squared, so the answer in x is sine of x squared plus c. Always check by differentiating the derivative with respect to x of sine of x squared by the chain rule is cosine of x squared times 2x. That's the original integrand. We're done. Notice what just happened. The chain rule, run forwards on sine of x squared, gave the derivative 2x times cosine of x squared. The chain rule, run backwards on 2x times cosine of x squared, gave back the antiderivative sine of x squared. Substitution is literally that loop. Second example. Compute the integral of quantity 3x squared plus 1 to the fifth times 6x dx. Same diagnosis. There's a composition, something to the fifth power, where the inside is 3x squared plus 1. The derivative of 3x squared plus 1 is 6x, and 6x is sitting right there as a factor in the integrand. The setup is begging for substitution. Let u equals 3x squared plus 1. Then du equals 6x dx. Substitute, the quantity 3x squared plus 1 to the fifth becomes u to the fifth, the 6x dx becomes du, and the integral is just the integral of u to the fifth du. That's a power rule integral, u to the sixth, over 6 plus c. Back substitute quantity 3x squared plus 1 to the sixth over 6 plus c. Done. Pause for a second on what we avoided. Without substitution, the only honest way to do this integral is to expand quantity 3x squared plus 1 to the fifth using the binomial theorem. That's 11 terms once you multiply through by the 6x, every term being a power of x, and you'd integrate each one with a power rule and sum them up. It works eventually, but you'd burn a page on it. With substitution, you write u equals 3x squared plus 1, the integral collapses to the integral of u to the fifth, du, you do it in one line, and you back substitute. The composition structure that made the polynomial expansion horrible is exactly the structure substitution was designed to exploit. Third example. Compute the integral of x over quantity x squared plus 1 dx. Look for the structure. The denominator x squared plus 1 is sitting inside a 1 over u shape. Its derivative is 2x. The numerator is x, so the derivative of the inside appears, but it's off by a factor of 2. That's fine. Constants are easy. We'll just track the factor. Let u equals x squared plus 1. Then du equals 2x dx, which means x dx equals 1/2 du. The original integral becomes the integral of 1 over u times 1/2 du. Pull the half out front, and you have 1/2 times the integral of du over u. That's another integral you should know cold. An antiderivative of 1 over u is the natural log of the absolute value of u. So the answer in u is 1/2 times the natural log of the absolute value of u plus c. Back substitute 1/2 times the natural log of the absolute value of quantity x squared plus 1 plus c. And one small simplification. X squared plus 1 is always positive for every real x, so the absolute value bars do nothing and can come off. Final answer, 1/2 times the natural log of quantity x squared plus 1 plus c. Notice the moral. The derivative of the inside doesn't have to appear in the integrand exactly. It has to appear up to a multiplicative constant. If your du is twice what's available, you just borrow a factor of 1/2 and slide it out front. If it's off by a factor of 7, slide a 1/7 out front. Constants in front of an integral are the easiest objects in calculus to manage. Variables in front of an integral are not. If what you needed was an x that isn't there, substitution won't save you. Fourth example, my favorite, because it illustrates something subtle that confuses students. Compute the integral of sine x times cosine x dx. The integrand has two obvious choices for u. Either factor's derivative shows up as the other factor, up to sine. Try it both ways. Way 1, let u equals sine x. Then du equals cosine x dx. The integral becomes the integral of u du, which is u squared over 2 plus c. Back substitute sine squared x over 2 plus c way 2, let u equals cosine x. Then du equals minus sine x dx, so sine x dx equals minus du. The integral becomes minus the integral of u de, which is minus u squared over 2, plus c. Back substitute minus cosine squared x over 2 plus c. We got two different looking answers, sine squared x over 2 and minus cosine squared x over 2. Did one of us make a mistake? No. Use the identity sine squared x plus cosine squared x equals 1. Then sine squared x over 2 equals quantity 1 minus cosine squared x over 2, which is 1/2 minus cosine squared x over 2. That is minus cosine squared x over 2 plus the constant 1/2. The two answers differ by 1/2, a constant, and the plus c at the end of an indefinite integral absorbs any additive constant. So both answers are correct. They describe the same family of antiderivatives written differently. Different starting constants, same family. This is the kind of thing that throws people off when they're checking their work against a textbook answer key. If you get an answer that looks different from the books, subtract the two answers. If the difference is constant, you're fine. Both answers are antiderivatives. Now, definite integrals, where there's one extra wrinkle. The substitution rule for a definite integral says, the integral from a to b of f of g of x times g prime of x dx equals the integral from g of a to g of b of f of u du. When you change variables from x to u, you also have to change the limits of integration from x values to u values. Why? It's just the fundamental theorem. Let capital F be an antiderivative of f. The left integral is, by the fundamental theorem, capital F of g of b minus capital F of g of a. The right integral is, also by the fundamental theorem, capital F evaluated at the top limit g of b minus capital F evaluated at the bottom limit g of a. Same number, same computation, different variable. So you have two valid strategies for a definite integral with substitution. Strategy 1, change the limits up front and work entirely in u, never go back to x. That's usually cleaner. Strategy 2, ignore the limits while you do the substitution, find the indefinite u antiderivative, back substitute to x, and then plug in the original x limits at the very end. Both are fine, pick one and be consistent. Quick concrete example to make the bounds. Changing explicit. Compute the integral from 0 to 1 of 2x times cosine of x squared dx. The integrand is the same one we did in example 1. Let u equals x squared, so du equals 2x dx. Now translate the limits. When x equals 0, u equals 0 squared, which is 0. When x equals 1, u equals 1 squared, which is 1. So the new u limits are also 0 to 1. That happened because g of 0 is 0 and g of 1 is 1. It's a coincidence of this example, not a rule. Usually the limits will change. Don't be lulled. The integral becomes the integral from 0 to 1 of cosine u du, which is sine u evaluated from 0 to 1, which is sine of 1 minus sine of 0. Sine of 0 is 0, so the answer is just sine of 1. A transcendental number, about 0.841. Notice we never had to back substitute. We changed the limits, did the antiderivative in u, plugged in the u limits, and we were done. For definite integrals, this is almost always the cleaner workflow. 3 kinds of pitfalls, and they bite essentially everyone the first time. For indefinite integrals, the most common mistake is forgetting to back substitute. You did all that work, you got a clean answer in u, you write the box around it, and the question was about x. Always back substitute. An answer in u is an answer to a different question. The other classic is forgetting the plus c. Don't. For definite integrals, there are 2 opposite mistakes and you have to avoid both. 1. You change variables, but forget to change the limits, so you end up evaluating an antiderivative in u at x values, which is meaningless. 2, and this is sneakier, you change the limits and back substitute to x before plugging them in. That's double counting the change and gives you the wrong answer. Pick one strategy, either change the limits and stay in u, or leave the limits alone and come back to x. Never both. For choice of u, the worst kind of u is one whose derivative just isn't in your integrand. If your du contains a factor that doesn't appear in the original integrand, you have no way to match it. You'll end up with leftover x's in your u integral, which is the visible symptom that something went wrong. When that happens, back out, try a different u. how to actually pick u when nobody is telling you. 2 heuristics, and they almost always point at the same thing. Heuristic 1, u should be the inside of a composition. If you see cosine of something, the something is a candidate. If you see e to the something is a candidate. If you see a square root of an expression, that expression is a candidate. If you see anything raised to a power, the base is a candidate. Heuristic 2, pick u, so that the derivative of u also shows up in the integrand, at least up to a multiplicative constant. If the derivative of your proposed u has no representative in what you're integrating, you can't match du, and substitution will go nowhere. Common candidates worth mentioning explicitly. If there's a denominator that's a polynomial, try u equals the denominator. If there's an exponent, try u equals the exponent. If there's an argument of a trig, xp, or log function, try the argument. If there's a big bracketed expression raised to a power, try the expression inside. And if your first u doesn't pan out, leftover x's, or du doesn't match, just try a different one. Substitution is cheap. You haven't lost anything except 30 seconds. Sometimes the right u is the second guess. Sometimes it's the third. Once in a while, it's none of them, and you reach for integration by parts, which is next episode. Recap. Integration by substitution is the chain rule running backwards. If your integrand has the shape f of g of x times t prime of x, then setting u equals g of x collapses the integrand to f of u du in the new variable, which had better be easier. The Leibniz differentials notation, du equals g prime of x dx, makes the substitution look like algebraic cancellation, and it works because of the chain rule we proved up front. Recipe, pick u, compute du, substitute, integrate in u, back substitute to x. For definite integrals, either change the limits when you change variables, cleaner, or keep the limits and come back to x before evaluating. Never do both. We worked 4 examples: 2x times cosine of x squared integrated to sine of x squared. Quantity 3x squared plus 1 to the 5th times 6x integrated to quantity 3x squared plus 1 to the 6th over 6 without ever expanding the polynomial. X over quantity x squared plus 1 integrated to 1/2 times the natural log of quantity x squared plus 1. And sine x times cosine x, done both ways, giving 2 different looking answers that differ by a constant, both correct. How to choose u, it's usually the inside of a composition, and you should pick it so that its derivative is also showing up in the integrand. If it isn't, try a different u. Next episode, integration by parts. The product rule, run backwards. Substitution and parts are the 2 structural techniques of integration, and together they handle almost every integral in a first calculus course. See you there. That's substitution. If this video helped, like the thing, leave a comment, and consider subscribing. It genuinely helps the channel grow, and it tells the algorithm that explanatory math videos are worth pushing to other learners. Drop your favorite hard integral in the comments, especially one where a clever choice of u saves the day. I read them. Next episode, integration by parts. The product rule, run backwards. Once you have substitution and parts together, you can hit almost any textbook integral in a first calculus course. See you in the next one. Substitution is the chain rule, run backwards. The next great technique, integration by parts, is the product rule, run backwards. Together, they handle most of the integrals in a first calculus course. If you want to see Leibniz's trick, the one that lets you integrate the natural log of x, arctan x, xe to the x, and a dozen other integrals that look hopeless until you split them, subscribe, and I'll see you there. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.